Welcome to the Institute of Aeronautical Engineering. This is Shravanti from Information Technology and I am going to discuss about the topic recurrent neural networks in a time series prediction. Coming to the introduction to recurrent neural networks, RNN or a class of neural networks designed to handle sequential data by maintaining a hidden state across time steps. They are particularly effective for tasks where context and temporal dependencies are important. RNN have been widely applied in a time series prediction, natural language processing, and speech recognition. This is the introduction about the recurrent neural networks RNN. Next, what is time series data? Time series data consists of sequential sequences of data points collected or recorded at successive points in time. Examples include stock prices, weather data, and economic indicators. These are some of the examples of time series data like stock prices, weather data, and economic indicators. Accurate prediction of future values relies on understanding the temporal dependencies within the data. This is all about the time series data. Next, coming to the basic architecture of RNN. RNN consists of loops within the network, allowing information to persist from one step to the next. Next, the core components is the recurrent cell, which updates its hidden state based on previous state and current input. This structure enables the network to model temporal dependencies effectively. This is all about the basic architecture of RNN. RNN consists of the loops within the network allowing information to persist from one step to the next. The core component is the current cell, which updates its hidden state based on a previous state and current state. This structure enables the network to model temporal dependencies effectively. Next, coming to the challenges with the traditional RNN. Traditional RNN can struggle with learning long-term dependencies due to issues like vanishing and X-loading gradients. These problems hinder the network's ability to learn relationships across distant time steps. As a result, training deep RNN on long sequences becomes difficult and less effective. These are the challenges with traditional RNN. Next, long short-term memory LSTM networks. Long short-term memory. Here, in a long short-term memory are a types of RNN designed to overcome the vanishing gradient problems, and they introduce gating mechanism like input, forgot, and output gates to control information flow. And LSTMs are highly effective for capturing long term dependencies in a series data. This is all about the long short term memory LSTM. LSTM are a type of RNN designed to overcome the vanishing gradient problems, and they introduced gating mechanism, input, forgot, and output gates to control information flow. LSTM are highly effective for capturing long-term dependencies in a time series data. Next, coming to the gated recurrent units. Gated recurrent units GRU are a simplified version of LSTM with fewer parameters and mechanism gating mechanisms. They combine the forgot and input gates into a single update gate, making them computationally efficient. GRUs perform well in a many time series prediction tasks often comparable to LSTM. This is all about the GRUs, gated recurrent units, or a simplified version of LSTM with fewer parameters and gating mechanisms. They combine the forget and input gates into a single update gate, making them computationally efficient. GRUs perform well in many time series prediction tasks, often comparable to LSTM. Next, coming to the training RNN for time series prediction. RNN are trained using back propagation to the time BBTT, which unrolls the networks across sequences. Proper data processing, such as normalization, is crucial for effective training. Loss functions like mean squared error MSE are commonly used to assess prediction accuracy. This is the training of RNN for time series data. Firstly, RNN are trained using back propagation through time, and which enrolls the network across sequences. And next, proper data preparation pre-processing, such as normalization, is crucial for effective training. Loss functions like mean squared error are commonly used to assess prediction across accuracy. This is how the training for time series prediction. RNN are trained using back propagation through time, which unrolls the network across sequences. Proper data pre-processing, such as normalization, is crucial for effective training. Loss functions like mean squared error are commonly used to access prediction accuracy. Next, coming to the applications of RNN in a time series prediction. RNN are used for financial forecasting, such as stock price prediction. They are applied in weather forecasting to model climate patterns. RNN also assist in energy loading forecasting and anomaly detection in a sensor data. These are the applications of RNN in a time series prediction. Next, coming to the advantages of using RNN in a time series. RNN can capture complex temporal dependencies that traditional models may miss. They adapt well to varying sequence lengths and irregular time intervals. RNN can incorporate additional features to improve prediction accuracy. These are the advantages of RNN in time series. Next, the limitations of RNN. RNN can be computationally intensive to train, especially with long sequences. They are prone to overfitting and require large datasets for optimal performance. Handling very long sequences remains challenging despite advanced variant like LSTM and GRU. These are some of the limitations of RNN. Like RNN can be computationally intensive to train, especially with long sequences. They are prone to overfitting and require large datasets for optimal performance. Handling very long sequences remains challenging despite advanced variant like LSTM and GRU. Next, recent advances and variants. Attention mechanism and transformer models have been integrated with RNN to improve long-term dependency learning. Hybrid models combining RNN with other machine learning techniques are gaining popularity. Advances in hardware and optimization algorithms continue to enhance RNN training efficiency. These are the recent advances and variants. Next, coming to the practical consideration Practical consideration: proper hyperparameter tuning is essential for optimal RNN performance. Ensuring high quality, well processed data significantly impact prediction accuracy. Model interpretability can be challenging but is crucial for decision making in crucial applications. These are the practical considerations. Coming to the conclusion and future directions, RNN remains a powerful tool for time series predicting, especially with ongoing innovations. Combining RNN with other deep learning architectures can address current limitations. Future research is focused on improving scalability, interruptibility, and handling of irregular data. This is the conclusion of our topic. This is all about our topic, recurrent neural networks in a time series prediction. And thank you.